Pluto is a distant and perplexing planet, which was once considered part of our nearby planetary family. However, ongoing disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a shocking exposure. They suggest that this chilly world is on a potential intense collision course with Neptune. Yet how is it that this could work out, and what may be the consequences of such an enormous event? Are we seeing an intriguing, impossible-to-miss occurrence? Or is there something else to this moving toward a huge accident? Join us as we examine the possible outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downsized to a dwarf planet mostly because of its eccentric orbit, remains a subject of interest and study in the cosmic community. Recent estimates by leading analysts indicate that Pluto's orbit is hazardously near Neptune's. Tyson and Kaku are both raising the alarm about a potentially hazardous collision between these two planets, which could pose a monstrous danger to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our nearby planetary group. It requires a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. The interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more strange is its inclination, tilted at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets, and this inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most interesting parts of Pluto's orbit is its convergence with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, going against what we might expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, cosmologists tried to sort out its unusual path. Unlike other planets whose orbits lie somewhat close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The stability of Pluto's orbit amidst these intricacies is evidence of the complexities of celestial mechanics. The three-body problem in space deals with determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all interact in a complex way. The terms Amal libration and degree libration, alongside the VZK oscillation, are fundamental parts of this riddle. According to astrophysicists, what keeps all planets in their orbits is Amal libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from converging. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes nearest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an extra layer of protection from potential impacts. Another key piece of this situation is the VZK oscillation, named after three researchers who studied how objects move in space. It refers to how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move, and in Pluto's case, the VZK helps us understand why its orbit around the Sun is so peculiar. Despite Pluto's path appearing turbulent, this oscillation aids in keeping it moving smoothly for extended periods. The VZK oscillation shows that even when things in space seem wild and random, certain patterns and rules maintain some control. All these variables help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or wander off course. This three-body problem helps us figure out how these factors change based on how these space objects pull on each other. Studying this helps us learn about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stabilizing properties, Pluto's orbit is actually chaotic, with slight deviations in initial conditions leading to significant differences over millennia. However, these unique properties of Pluto's orbit have been found to maintain stability over extraordinarily long timescales. Still, monitoring the chaos is essential. Later virtual simulations have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto whereby for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path predictable. However, Neptune isn't the only one aiding in this. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for quite some time. Indeed, even billions of years. So it appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are vital in the broader context of the universe, maintaining the order and consistency of celestial bodies' movements. Without these components, our solar system would be a much more tumultuous and chaotic place. Bodies like Pluto might actually collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, particularly with discussions about it possibly crashing into Neptune in the future, understanding its orbit is very important. It gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most apparently unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also shows the significance of continuous observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the whimsical nature of celestial bodies, and Pluto's orbit is an ideal representation of this eccentricity. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly outlined in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can dramatically change its long-term orbit. Utilizing virtual simulations has been incredibly helpful for researchers to figure out how Pluto moves in space. These simulations use advanced mathematics to demonstrate how Pluto and other space objects, like Neptune, pull on each other. By changing small details in the simulations, astronomers can see how even minor changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations uncovered something truly fascinating about Pluto's orbit. Despite having factors like Amal and degree libration to keep it stable, its path can still be chaotic and unpredictable. If you start with just a small difference in where Pluto is or how fast it's moving, over many years its orbit can end up looking quite different. However, even with this chaos, Pluto's orbit remains stable for long periods, like billions of years. This means Pluto's journey around the Sun has some kind of order to it, even though it may seem chaotic at first. Predicting future events, especially when they involve volatile orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often filled with uncertainties. While numerical simulations provide a robust means to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions and the complexity of the interactions they replicate. Any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe is still limited. Understanding the gravitational impacts of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential collision between Pluto and Neptune, despite all these complex forces trying to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the obscure realms of space. His position on Pluto's renaming is rooted in the ever-growing knowledge of our solar system. He sees the renaming not as a downgrade, but as a significant shift in our understanding of the numerous bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He views the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, especially the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. Tyson's work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often capricious forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with cutting-edge visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's views on Pluto and its orbit emphasize the need for continuous observation and advanced modeling to predict and understand potential celestial events. He sees the interactions between celestial bodies as a crucial area of study, not just for academic interest, but for practical implications. The potential collision between Pluto and Neptune, for instance, isn't just a theoretical scenario. It's a reminder of the dynamic and often tumultuous nature of space. Kaku's futurist perspective urges us to consider the broader ramifications of such events, from the impact on our understanding of the solar system to the possible need for future space interventions. His perspective highlights the importance of being prepared for the unexpected in space. His work suggests that the more we grasp the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of astronomical events. Both Tyson and Kaku's viewpoints converge on the idea that space is a realm of infinite discovery and that our current understanding, while substantial, is still limited. Their emphasis on the need for ongoing investigation and advanced modeling reflects the evolving nature of space science. They highlight the importance of not just understanding celestial mechanics as they are today, but also speculating on how they may change in the future. The potential collision between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for rigorous scientific inquiry, advanced technology, and a willingness to adapt our understanding as new information arises. For Tyson and Kaku, the mysteries of space exemplified by Pluto's orbit are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for many years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational influences acting upon them. Thus, a direct collision between Pluto and Neptune is highly unlikely. However, the complexities and potential nuances in orbital dynamics mean that cosmologists should continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they could present. While the probability of a Pluto-Neptune impact remains largely hypothetical and considered unlikely with our current understanding, it highlights the importance of continuous investigation and observation in space science. Advances in technology, including more advanced telescopes and virtual simulations, will assist astronomers in refining their models and predictions, ensuring we stay abreast of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both underscore the need for continuous examination and a flexible understanding of our universe. The potential collision scenario, while representing the dynamic and complex interactions within our solar system, ultimately reminds us of the vast yet still unknown areas in our comprehension of space. Through ongoing investigation and observation, we strive to unravel these mysteries, ensuring that our understanding keeps pace with the ever-evolving universe.